Hello everyone, welcome to our project, Dynamic Dual-Pivot Quicksort. My name is Fausto Preciado.
My name is Ruoping Gao.
And I'm Harbhajan Singh.
The motivation for our project comes from current quicksort and dual-pivot quicksort problems. So one of the problems is that the time complexity is sorted and unsorted list comes in O(n) squared. Pivots is selected using a constant index. And then possible performance improvements would be parallel computing, which is expensive, and select the pivot based on the content in the list. Dynamic dual pivot quicksort, which is our approach, our algorithm, proposed algorithm. Quicksort uses two pivots, uses mathematical operations to calculate the pivots at each iteration. This equally sized partitions equals better time complexity. Dual pivot approach. So the best performing approach, which is the Yaroslavsky's algorithm, and then our approach, which is the dynamic dual pivot quicksort. So both of them implement two pivots. And then for the Yaroslavsky pivot equals low and high. But for our approach algorithm, for our dual pivot quicksort, it's pivots calculated using the mean.
Okay, so here's how we do the dual pivot partitioning. So we are going to select two pivots, and we swap to get the required arrangement in the following diagram. And also we use the pivots that we pick to create three partitions, namely P1 and P2, for which P1 divides the part that for the elements that are less than P1 and those that are between P1 and P2, while P2 diverges those that are between P1 and P2 and those that are greater than P2. And here's how we calculate the pivot using the mean value to calculate the virtual pivot. So for the given case, we have a reversely sorted list from 8 to 1. So the first thing that we do is to divide it into halves. And then for the first half, we find the min and max values. And then also we do the same thing for the second partition, which is there we also find the min and max values. And at the end, we just add them all up and then divide them by the number of pivots, which is 4. And therefore, in this case, we have 4.5 at the virtual pivot. Time complexity best case. So the best case occurs when the virtual pivot ends up being in the median of the list, because this is going to divide the list into equal partitions at each iteration. And therefore, because it results in equal partitions, we therefore deduce the following recursive relation. And through solving this relation, we get the time complexity of O(n) log n for the best case. For the average and worst case, in an average case, the virtual pivot can be anywhere but the extreme positions in the list. And this is the result of the calculation method of the pivot. The average and the worst case analysis are combined together, and there is no exact recurrence relation that could be determined at this point. And one possibility is to perform heuristic analysis in order to find the average index of the pivot in all the cases, which is included as part of our improvement plans.
So, comparison with other similar quicksort methods, the key feature of our algorithm focuses on very specific cases, because we're trying to target those cases where the current quicksort variants fail. I mean, they don't fail, but they just take longer. And those specific cases are the sorted lists and the reversely sorted lists. In the table, we can see all the time complexities for these specific cases. And then we see that dynamic dual-pivot quicksort has the best time complexity among the three, which is big O of n log n. And here are the experimental results, which are basically the runtimes in seconds that each of the algorithm takes for a specific sized list. And then the green highlighted boxes show the best runtimes for that particular size. And then the same thing with the sorted lists. And then we see that in the reversely sorted list, the calculated pivot quicksort, which is the dynamic pivot quicksort, does really well. Then it outperforms the other two algorithms, but in terms of the sorted lists, it does almost, it runs in at the same time or almost the same time as that of the Dual-Pivot Quicksort.
Conclusion. In this project, we were able to show how dynamic, not fixed pivots improve the time complexity of quicksort algorithm. Additionally, having more pivots help us attain more partitions, in ideal case only.
The proposed algorithm outperformed the current quicksort variant in the desired cases, both sorted and reversely sorted lists.
It also shows a better time complexity, which is n log n when compared with the other quicksort variants, which is n squared.
Further improvements can be made to the calculation function to calculate pivots in a more efficient and quicker manner. Main bottleneck.
That's it for our presentation. Thank you.
Thank you.
Thank you.